All right, so in the last video, we wrapped up with an example that included conditioning for continuous random variables. So let's actually develop this more fully. So we're going to talk now about a modeling framework for conditioning with continuous random variables. So remember, again, that the conditional probability of seeing an event A, given that event B occurs, is the probability of A given B, which is the probability of the intersection of A and B divided by the probability of B, assuming, as always, that probability of B is greater than 0. And also remember, for a continuous random variable x, we can calculate the probability that x lands in the set A via the PDF. All I do is integrate over the set A for the PDF, okay? So is there a way that I can calculate the probability that x lands in A, given that I already know that it lands in B, using some kind of conditional PDF? So what I want to be able to do is write the conditional probability of x in A given x in B as the integral of something that I'm going to call the conditional PDF of x given B. And all I want to do is integrate that over A. And the answer is, well, I have this video, so it's just yes. And so the conditional PDF f of x given B of the random variable x, given the event that x falls into B, is the following. So I define it as two cases. So at first I have the PDF of x divided by the probability that x falls into B when x is in B, 0 when it doesn't fall into B, and this denominator I can work out as the integral of the PDF over B. Okay, that's by additivity. Okay, so this is our formula for the conditional PDF. Previously, we had worked out why things like this are true. Here it's a little bit trickier. I would first have to work out the conditional CDF and take derivatives carefully. You can look at your lecture notes for more details. I'm not going to do that here. Okay, so to figure out the probability that x lands in A, given that we know that it lands in B, I can just plug into the conditional PDF, assuming that I've already worked it out. Okay, so what I'm going to do is I'm going to say, well, what I want to know is probability of x in A, given that x is in B. I integrate over A for the conditional PDF given B. And what is that? Well, we just define it to be the PDF divided by the integral over B when x is in B and 0 otherwise. Okay, so that's the thing we just defined on the previous slide. Okay, let's think about what should happen here. So I'm already integrating over A, and I know that x is only going to be allowed to take values in B. So the only places where this is going to be interesting is A intersect B. So the parts of A that also fall into B. So what I'm really doing is integrating over A intersect B, the PDF, and dividing by the integral over B. And this resembles this idea that I have the probability of the intersection divided by the probability of just B. Okay, let's do an example to see what this means. First, I'm going to draw a PDF. I'm not going to specify it in terms of an equation. I'm just going to draw some triangles, and we'll use our old half base times height to get areas. So let's let B be the event that it's, or the set 1 to infinity. Okay, and I want to work out the conditional PDF of x given B. My first step is going to be okay, I'm just going to draw B. So there's B on my axis. It starts at 1. And my first step is going to be to determine the probability that x falls into B. Okay, this red set. And the way I'm going to do that is just integrate over B the PDF. Okay, so here I have it. And as I said, we're not going to use formulas here. We're just looking at these triangles. So we all know that the area of a triangle is half base times height, right? So half times the base of the triangle times the height. So in this case, if I look at the triangle, which is over B, it's just going to be half times its base, which is 1, times its height, which is 2/3. Because you can see that starting at 1, if I go up, I have the height of 2/3. And so this is just going to be 1/3. That's the area over B. Okay? Now, the second thing I'm going to do is I'm going to calculate the conditional PDF by just plugging into the formula. Okay, so the formula is the PDF divided by the probability that x falls into B. And that's going to be true whenever x is actually in B. That's my condition. And it's going to be 0 otherwise. Otherwise, it can't happen. Okay, so we're not going to follow this again with the formula. We're just going to draw it. Okay, so what should happen is I should have the same basic shape that I had in the PDF, but it should only be active over B. So we're going to draw something like that. And I'm going to notice it's going up all the way to 2 and then heading back down. And the reason for that is that I had to divide by a third in order to renormalize the PDF. So that was this divide by the probability of x falling into B. So now I go from height 2/3 all the way up to height 2. And this red triangle is now the conditional PDF of x given B. Okay, finally, let's let A be the interval from half to 3/2, and let's use the thing that we had above to calculate a conditional probability. Okay, so here is A. It's between half and 3/2. So what I want to be able to do is determine the probability that x falls into A, given that I already know that x is going to fall into B. The formula above tells me that what I need to do is integrate the conditional probability of x given B over A intersect B. Okay, so that is this area that I've highlighted in purple here. Okay, so I want to know this area, and okay, it's not quite a triangle, but I can notice that it's the complement of a triangle. So I'm going to write this instead as 1 minus half base times height. And the triangle that I'm thinking of for base times height is the one from 3/2 to 2, right? So the height of that triangle, so there's that triangle. So I'm just subtracting the area of this triangle from 1. So I get 1 minus a half times a half. That's the base of this triangle, and its height is 1. So overall, I get 1 minus a fourth, which is 3/4. Okay, so that was a quick example of calculating conditional probabilities. So once we have conditioning for the PDF, we should also work out conditional expected values as we did before. And remember, the idea is just to replace sums with integrals. So the conditional expected value, E of x given B, so it's of x given the event that it already falls into B, that is defined to be the integral over B, x times the conditional PDF given B. And I can think about this as, if I want to just write it directly using the PDF, as the integral over B, x times the original PDF, divided by the integral of the PDF only over B. Okay, so that's just kind of expanding this a little bit. Okay, so that's my first formula. I can do the same thing for functions. We've been doing this for a while. Conditional expected value of of g of x, a function g of x, given that x falls into B, that is going to be the expected value of gx given B, and that's the integral over B gx PDF condition on B, and that's just going to be the integral of gx PDF over B over the integral of the PDF over B. And finally, we can also talk about the conditional variance of x given B, and in fact, we don't need to write anything differently than we've had before, because we already defined how to take conditional expected values using integration, so I'm just writing the same formula that I had before. The thing I want to highlight for you here, that again, we talked about this with discrete random variables, it's a little tricky, is every time the expectation appears in this variance formula, I have a condition on B. Okay, and I can see that there. I also have this alternate formula, so I have e of x squared given B minus the square of e of x given B. Okay, so that's the definition of the conditional variance, and that's something we can look back to. Okay, let's close out with a longer example. So we're going to just take a uniform distribution. In this case, we're going to say x is uniform over minus 1, 1. All right, and I'm going to condition on the event that the absolute value of x is greater than or equal to a half. Okay, that's my event. So here's the first thing that I want to do. What is the conditional PDF? Well, I need to first remember the formula, and I'm going to just draw the PDF so I have something to reference and talk about. So the original uniform distribution is between minus 1 and 1. So what is the height of that going to have to be in order to normalize to 1? The height is going to be 1/2, so that I have a box of height 1/2 and width 2. So that's area 1. And these regions here are the regions where B is active, right? So where the absolute value is less than or greater than or equal to 1/2. Okay, so this is the region B. So the integral of B, the thing that I need to know, so the integral over B of the PDF is just the area, and it's obvious from looking at this plot that that's just half of the total area, so that's half, because everything normalizes to 1. Okay, so now I can actually just draw the conditional PDF directly. Okay, I don't need to work out the formula. even though I could have done it working case by case from the formula, what I can do instead is just say that, well, on the regions where x falls into B, I'm going to have the same shape of the original PDF, but I'm going to rescale it. So here I go. I rescale it, so it goes up to 1, and then when x is not in B, I just have 0. Okay, so what I've gone here is I have these two boxes where x actually falls into B, and the height has changed, okay? So the height of f of x given B is going to be, in this particular case, twice that of the height of the original PDF. And the reason I have to do that is so that the total area remains 1. Remember, conditioning is just like shrinking the universe in which things can happen, but I'm still living in this probability framework, so the total area has to be 1. So in this case, I divide it by 1/2, which is like multiplying by 2. Okay, I could have also done this from formula, so let's do it the other way. So I'm going to write the definition of the conditional PDF. So that's f of x over the integral of f of x over b. That's when x is in b, and 0 otherwise. Okay, so what is the integral of f of x over b? We did this visually, but let's do it formally. So I have from -1 to -1/2 of 1/2 dx plus the integral from 1/2 to 1 of 1/2 dx. Okay, so that's just going to be 1/4 plus 1/4, and I'm going to get 1/2, just as I saw from the picture. So I plug in back into this formula above. I'm going to get 1/2 divided by 1/2 whenever x is greater than or equal to 1/2 in terms of its absolute value and 0 otherwise, and therefore it's just going to be 1 when the absolute value is between 1/2 and 1 and 0 otherwise. Okay, so two ways to calculate the same thing. In this case, the plot was probably more intuitive, but it's good to also be familiar with how to use the formulas because sometimes you can't work directly from the plot. Okay, let's stay with this same example and let's go and calculate some conditional expectations. Okay, so now I've just shifted the conditional PDF up and I want to get the conditional expected value of x given b. Okay, so the formula is integrate over b f of xb times x dx. And so I have from -1 to -1/2 x dx plus 1/2 to 1 x dx. Okay, so I'm going to write this out carefully, but let's just look at this plot and try to guess where the center of mass is. It's at 0. Okay, so what I should get from this calculation is 0. Well, let's go ahead. So I have 1/2 x squared from -1 to -1/2 plus 1/2 x squared from 1/2 to 1. So that's going to be 1/4 minus 1/2 plus 1/2 minus 1/4, and that's going to be 0. So I'm done. That got what I expected. Okay, let's also compute the variance. Okay, conditional variance, x given b. Okay, first thing I should do to make my life a little bit easier, so I'm just computing a simple expression, is first get e of x squared given b, and I'll use the alternate variance formula. So e of x squared given b, just the integral over b x squared times the conditional PDF. So that's going to be the integral from -1 to 1 -1/2 of x squared dx plus the integral from 1/2 to 1 x squared dx. So that's going to be 1/3 x cubed from -1 to -1/2 plus 1/3 x cubed from 1/2 to 1. So that's going to be -1/24 minus 1/3 plus 1/3 minus 1/24. So putting everything over 24, I have -1 plus 8 plus 8 minus 1/24, and that works out to be 7/12. Okay, so now I can use my alternate variance formula. Variance of x given b is going to be e of x squared given b minus the square of e of x given b. So we already worked that out. And that's going to be 7/12 minus, in this case, 0 squared. So again, 7/12. Okay. And finally, let's say what I want to work out is the expected value of 3x minus 1 squared given b. Okay, so this is something a little different than what we've seen before, but it turns out we don't need to do a lot of work. So we could get this directly by just plugging in this function 3x minus 1 squared into our formula, but we actually already have all the ingredients we need to calculate this without doing any more integrals. So first, let's expand the square. So I'm going to get 9x squared minus 6x plus 1 given b. Okay, And now, so this is the trick. And this is where linearity of expectation is super useful. I can write this as 9e of x squared given b minus 6e of x given b plus 1. Okay? And this is actually by linearity of expectation. I can always pull apart these sums of terms. So then I have all of these terms worked out. I have 9 times 7/12 minus 6 times 0 plus 1. Putting everything over 12, I get 63 plus 12 over 12. That's going to be 75 over 12, which is 25 over 4. Simple. Okay, so sometimes when you see an expression that looks a little bit more complicated, think for a moment to see whether you might already have some of those ingredients and whether you might be able to use a property, especially like linearity of expectation, to simplify your calculations.